Okay, welcome everybody to the Mathematical Physics Seminar, the first in-person event this semester. And I'm happy to welcome Professor Boris Hanin from Princeton University. And he will speak today about random neural networks at finite width and large depth.
Okay, thanks very much for the introduction, Marcus, and I appreciate the invitation. It's nice to start traveling again and talking to people in person. You always get more information that way somehow than over Zoom for reasons I can't quite explain. Okay, so I want to tell you about a kind of circle of ideas I've been really excited about the last couple of years. And obviously it has to do with neural networks. But I want to first acknowledge my collaborators. So there are three people who helped with various parts of this work. Two of them are young physicists who I really like, named Dan Roberts and Yaida. So Sho is at Facebook AI. Dan is affiliated with MIT and also with Salesforce. And then there's a mathematician that's really great too, also a young guy named Mihai Nika. He's at Guelph right now. And they help with various parts of this. And in particular, so a lot of what I'm going to say is based on parts of a book that Dan and Sho and I recently wrote. So they did the writing, I helped with the research, that's the attribution. And it's too long to sort of say everything, but I'll gesture at a lot of the things that are in there. Okay, so I'm going to talk about random neural networks, but I don't want to assume everyone already knows what a neural network is. So I'm going to start by trying to give a definition of a neural network on this board, which is why I didn't divide it up. And if I try to erase it, you need to yell at me and tell me not to do it, because sometimes I forget and it's going to be a disaster. Okay, so a neural network at some high level is just some finite dimensional family of functions. Okay, and I need to tell you what kind of family of functions it is. So here I go. I'm going to start drawing the picture and writing the formula. So pictorially, neural networks are built up out of neurons. So I'm going to start by telling you what a neuron is. Okay, so a neuron is a kind of computational unit, and you think of it like this. It takes an input x in a space that, for reasons you'll understand in a second, I call Rn0. So n0 is called the input dimension. And each of these dots is meant to represent a single scalar, which in this case are just the components of the input. Okay, and then what does a neuron do? Well, a neuron is also a dot, but it's a different kind of dot. Okay, so a neuron has associated to it a bunch of weights. These are scalars, W1, W2, down to Wn0, one for each input. And it also has a single bias, which I will call B. And then what does the neuron do? It takes the dot product of the vector of x's with the vector of w's. It adds b to it, and it outputs your favorite nonlinear function, sigma, applied to w dot x plus b. Okay, so that's what a single neuron does. It's a way of returning a function from some specified dimensional space to R, and it's just an affine transformation of x, and then you apply your favorite nonlinear function to it. Okay, so this was invented in the late 40s by Frank Rosenblatt as a kind of very simple and wildly inaccurate model of what neurons in the brain are supposed to do. Okay, so that's what a single neuron is, and now I have to tell you what a layer of neurons is, and that's why I sort of drew it in this funny way. A layer of neurons is just a bunch of neurons that share the same input. Okay, so now I'm going to start promoting the notation. So now I'm going to have potentially some large number of neurons. It's going to be large for me. And I think of these weights as W11, W12, W1, and this being W1, and this being B1. And now I have lots of neurons. This neuron computes sigma of W2 dot x plus B2, all the way down to sigma of Wn1 dot x plus Bn1. In other words, mathematically speaking, what are we doing? Okay, we just have a linear transformation from Rn0 to Rn1. So x maps to what I'll call z1 of x, which by definition is just w times x plus b. W is just the matrix whose rows are these vectors, and b is the vector whose components are these scalars. That's what each neuron sees, and then you apply sigma to each component of the vector. And you get a function that goes from Rn0 to Rn1. Okay, that's what a layer of a neural network is. And now a neural network is simply given by a composition of such layers. Okay, so that's why I left a lot of room, and why I need to promote the notation one more time. Okay, these are the weights and biases, so-called in layer 1. So this is the matrix of weights in layer 1. This is the vector of biases in layer 1. I won't bother to promote all the rest of the notation. And now in the next layer, you have some other space that you map to. So now you get z2 of x, and this is given by w2 applied to sigma of z1 of x plus b2. And this is in Rn2 now. I have n neurons in this second layer, and they all have their weights going in and they have their weights going out. And I simply repeat this procedure some number of times of apply affine transformation and then apply sigma to each component that you get. And I will call the final layer zl plus 1, so eventually I map to z capital L of x. That's what happens after I apply my nonlinearity capital L times, and my final layer will be z capital L plus 1 of x. That's the output of the network. And this is just WL plus 1 applied to sigma of ZL plus BL plus 1. And I don't apply sigma in the last layer. Okay, that's just my convention. And this is what I mean by a neural network. And okay, whatever this thing is, I at least have not been a complete cheat and liar, in the sense that this is indeed a finite dimensional family of functions. Okay, it is determined by the so-called architecture. That's these dimensions of the hidden layers, so-called. These n's. Okay, I guess I didn't write, but this, of course, is in R and L plus 1. So it's determined by these numbers. The number capital L is called the depth of the network, number of layers. And then sigma is fixed. And the parameters of this family of transformations from Rn0 to Rnl plus 1 are indeed the biases and weights of the network. It's actually the affine transformations themselves. Okay, so by varying the affine transformations in each layer, you obtain some potentially very high dimensional family of functions. All right, so let me just pause for 1 second and ask if there are questions about this, because if this wasn't clear, then the rest of the talk is hopeless. But I want to, yeah.
So the W's and B's are just, parameters that we're going to interact, right?
Yeah.
Right. Is there a reason why we have to choose sigma to be of the same form every time?
So that's an excellent question, often asked. And I choose, there's absolutely no reason it has to be of the same form. Almost always in practice it's of the same form, with the usual caveat that it's not of the same form when you need to do something else.
Okay.
And this seems to work well. And it's not clear that varying the sigmas can be done in some systematic way to be of use, but that's not to say that it can't be done in such a way. So yeah, I think it's a totally reasonable question. I'm going to hopefully leave that up there so that we can marvel at the neural network. Okay. Other questions? Yeah.
You said finite dimensional a couple times, but that's not in a linear space.
Yes, indeed. So it is not finite dimensional linear space, but it's a finite dimensional space.
Okay.
And I mean, it's good that it's not linear. Otherwise, I can only compute linear functions, and that'd be pretty sad. But yeah. Okay, we're going to come back to that in just a moment. So you're totally right. Okay. So let me go on. Okay. So I told you now what a neural network is, and the whole point of my talk, at least most of it, is going to be to try to understand the properties of this thing when the weights and biases are chosen at random. Okay, in order to explain why that's an interesting thing, I need to tell you how neural networks are used in practice, because that will motivate this kind of study of random neural networks. Then I'll try to state some theorems. Some of them will be physicsy theorems, so the book I wrote with Dan and Sho was a physics book, so not everything is proved in a purely mathematical way, though doubtless it's right. And then some of the things I'll state are mathematical, and I'll try to distinguish little by little. Okay, so I need to tell you the typical use of a neural network. Right? What do you do with such a monster when it is presented to you? I mean, potentially the answer is you run away, but hopefully you do something more sensible. Okay, so in my mind, the typical use is broken down to 4 or 5 steps, which I'm going to recapitulate now. Okay, so step 1 is what I think of as data acquisition. So data acquisition simply means you go out in the world and you observe some phenomenon happening and you get some point observations. Okay, so this means you collect some inputs xi and some correct outputs, or maybe approximately correct outputs, f of xi. So I goes from 1 up to the number of data points you collect. And maybe a good example to think about is xi is an MRI image or some kind of medical image that you have, and f of xi is whether or not there's a tumor in the image. It's the kind of thing where a trained professional can often correctly classify whether or not there's a tumor, although it can be time intensive. But if you want to write down a formula for f, it's complicated because, the image is basically a bunch of pixels, and it's not clear how to combine the pixels into a formula for f. And indeed, our goal is to learn an approximation to f using a neural network. That's where we're going. Okay, so but this is typically step 1, and this is the beginnings of supervised learning. Okay, step 2 is once you have some data, you try to posit a class of functions that you're going to use to approximate f. So this is what you might call model selection. And model selection, at least in this simple context, these are the simplest kinds of neural networks called fully connected, feed-forward. Okay, there are more complicated ones used in practice, but it's to fix the hyperparameters of the model. Okay, so you fix the number of layers L, the dimensions of the hidden layers N1 up to NL, and sigma, let's say. Okay, typically N0 and NL plus 1 are fixed for you by the data themselves. So you generally don't vary those. Okay, and what does this do? As we were already discussing, this gives you some interesting, maybe I'll put it over here for continuity, nonlinear space in general of functions that you can compute using your neural network. Okay, so this is meant to be my picture of a manifold of functions that you can actually compute. So each point here represents one particular choice of the w's and b's, and some particular function. Okay, and the dream is that somewhere in this space, maybe right here, is a good approximation to your unknown function f. Okay, so our goal is to learn this approximation, and the third step in this procedure is the first part really where the randomness comes in, although the data itself is often random as well. So but more relevant to this talk is step 3, which is initialization. So this basically says, well, I have no idea where this putative approximation to my function f is, so I'm going to take a random guess. So you randomly choose the weights and biases, and for the purposes of the talk, this is basically how everyone does it in practice, so I'm just going to adopt this convention. So the weights in layer L are chosen from mean 0, variance CW over NL minus 1 Gaussian. You see, CW is going to be a constant whose role will be apparent soon, and NL minus 1 is the width of the previous layer. So let me sort of make an illustration here. You see, each neuron, for example, this one, has number of weights going into it called the Hanin equal to the width of the previous layer. And so the more neurons you have in the previous layer, the smaller you want each of the weights to be. And the correct scaling is like the central limit theorem scaling. And that's why I chose that variance. Okay, so and then similarly you choose the biases, B, L, I, each of them mean 0, variance, CB, Gaussian. Okay, all of them are independent. I'm not writing it, but yeah.
You're describing a sort of supervised learning problem, right?
Yeah.
You know, all the aspects like. Is any of what you're going to say sort of general to unsupervised or reinforcement learning problems, or necessarily just?
So the truth is that almost all problems you solve using neural networks, whether they're supervised or unsupervised in some official way, are turned into a supervised problem. Okay. Because ultimately you need to have an objective you're going to minimize so you can apply automatic differentiation and optimize. Right. So in an unsupervised problem, it might be a clever a clever trick to figure out which f to put in here. Maybe f of xi is actually xi itself, for example. That would be a reconstruction problem. Right. But then ultimately you will still be doing this kind of okay, there are some exceptions, but I would say this is like 95% of what's out there or more. Okay. So to leading order, I think yes, it's okay to just think about this. Yeah. Okay, very good. So you see, okay, randomly choose, random neural networks. Okay. So that's going to be motivation number 1 for why to study random neural networks. Neural networks start their lives as random, and so you might want to know what happens. Okay, but so it'll be complicated to describe, although I'll describe some of it. And on a pictorial level, it's very easy. This just means on this space, I have some probability distribution. Here's its density from which I sample. And I sample from this thing, and that's my neural network at the start of training, that orange star. Now, it has nothing to do with the pink star yet, but we're about to get there. Okay, so of course, this doesn't know about my data, so there's no chance it fits F unless I was so miraculously lucky that I should probably be investing my money in the stock market, right? So step 4 is indeed to do optimization. So now that I have an initial guess, I'm going to improve my guess. So I'm going to improve the vector theta, by which I mean the collection of all the weights and biases in the network. So L goes from 1 to capital L plus 1 by, okay, usually some variant of gradient descent, but I'll be sort of very generic here. So what this means is that this here was a way of choosing theta of 0, and at time t plus 1, my parameter vector is what it was at time t, and then I take a small step in the negative gradient direction of some function I'd like to minimize. And let me tell you what this function L is. Okay, there are many different choices in the real world, but you can just think of L as being something like the sum over the data points, or maybe the average over the data points, of the error you make on each data point. So this is what I was supposed to get on the data point, and this is what my current model gives me on the data point. I should put it L plus 1 quantity squared. So here I'm emphasizing the dependence of the output of the model on the vector of parameters that I have. Okay, so the idea is you try to minimize this thing by taking small steps in the negative gradient direction of the loss function. And, okay, this is my favorite picture to draw because I don't know how to prove the theorem in vast generality, but theorems aren't required when you draw pictures. You know, you go on some journey, and you hope that that's pretty much what happens. Okay, so of course in practice you also want to see whether your network does well on data it hasn't seen and so on. But let me just stop here and say that this is practically how neural networks are really used. And the fact that they work at all is kind of wild. Okay, just to give you a sense, the number of parameters in this model, in some of the larger models we have in practice, might be hundreds of billions. Okay, so I'm doing optimization over roughly a space that has dimension 100 billion. And this function I'm trying to minimize is some truly unpleasant function in principle, which might have lots of bad local minima and issues that you run into whenever you take an optimization course. And yet somehow these things work. And so part of the magic of the subject is one needs a new language and new understanding to explain why such a thing should be possible, because it works so often in practice. Okay, so this is supposed to be the end of the introduction, so I'm going to pause and try to ask for questions again. And then I'm going to state, again, some motivations for studying random neural networks, and then I'll go more into the mathematics of what's going on. Okay, so are there questions or comments so far on what I presented? Yeah?
I guess, insofar as we're doing gradient descent, of course, we should worry about the local minima, but I guess you're going to say something about that and it doesn't get stuck there. But are we also assuming somehow that the space of parameters is somehow fully connected? Because otherwise, it's possible that any continuous update rule could get you to the right approximation.
Yes, so one thing is that this is not a constrained optimization problem. In practice, it is very rare to put bounds or any kind of conditions on the W's and B's. They're simply free parameters.
Okay.
And so nothing stops you if your model tells you to, for example, for some of these weights and biases to diverge, and sometimes they do, and obviously that's generally not a great thing.
Right.
But yeah, right. So it's not a constraint problem. Other comments or questions? Okay, so fine, very good. Okay, so let me give you a motivation for studying, well, 3 motivations really for studying randomly chosen networks. And then I'm going to draw one more picture that's meant to be an intuition for how to think about what is going on at some extremely high level with these networks, and then I will start stating some more precise results. Okay, so let me start the motivation over here. I lied, I'm going to start it over here. Okay, so motivation for random networks goes like this. Okay, so one piece of motivation I already basically told you, but let me write it for posterity. Okay, I want to understand what you might think of as the prior over functions at the start of training. You see, the distribution over the weights and biases I wrote down for you, and it's almost trivial. All the weights and biases are independent of each other, but that's not really what you care about. You care about which functions you get. And the distribution over the network outputs is a complicated distribution because the output is a highly nonlinear function of its parameters. So changing variables, so to speak, is not so easy, and I'm just trying to understand what kinds of functions am I getting when I start training. You could try to align that to the data you have. Maybe you want functions that have some properties that align with the problem you're trying to solve. Or maybe you just want to start near reasonable functions for numerical reasons. Okay, so that's kind of motivation number 1. Motivation number 2 is kind of like this. You know, in practice, you have to choose a lot of parameters. So in practice, we must choose a lot of things. So we have to choose the depth of the network, the widths of the hidden layers. We have to choose sigma. We have to choose these constants CB and CW. We have to choose the learning rates. There are many, many things you have to choose. And, you know, you would like to know what is the relationship between all of these objects, even at the start of training. You know, which depths and which widths and which sigmas and CBs and CWs give you something sensible. And you know, this is just a study of saying, independent of the data, I'd like to start with interesting but not completely pathological functions. And so in practice, a lot of times, there are many hyperparameters I'm not talking about here. You simply do something brutal like try a lot of them and see what happens. And that's very, very painful, both in terms of time and in terms of cost. And so it's nice to have principles for how things are supposed to scale together, and I'll state some of them in this talk. Okay, that's one of the outputs of our work. Okay, and then kind of as a last motivation, I'm going to be more precise about this in a moment. Studying random neural networks is actually not only about understanding what happens at the start of training. So for 2 reasons. One is philosophical, so I won't write it down, but I'll say it. You know, just like in random matrix theory, when you study large random matrices, you hope that maybe when an object is very complex, it looks like a random version of the object. Similarly here, even after training, you could hope that some coarse properties of your neural network are not too different than the way they started out. Okay, that's a kind of philosophical point, but more prosaically, it goes like this. So when the number of parameters in the network far exceeds the number of data points in the network that you use to train, and this is a situation which happens often, though not always. Okay, you can show, and let me put a big asterisk here, in the sense that you can show under certain important restrictions. This is just not always going to be true, but in some class of situations, you can show that training is given approximately by, and I'll make this precise in a couple minutes, linearization around the start of training, around theta of 0. So in some sense, all the action, all the difficult things are to compute statistics at the start of training. And the intuition is very vaguely like this. When you have many more parameters and data points, you don't have to move any one parameter too much to fit the data. So it's almost like Taylor expanding around where you started. Okay, it's a little bit of a faulty intuition, but nonetheless, there's something to it, and there's a precise result or two that I will state in this direction. Okay, so that's motivation. And let me give you one final bit of intuition, and then I'll stop, and that'll be the end of the non-mathematical portion of the programming, so to speak. Okay, so here's like in my mind, what one way in intuition, maybe that's how you spell intuition, to think about what happens. I'm going to specifically think about just the architecture, the depth and the width of the network. Okay, those are 2 fundamental parameters I get to use. Increasing the width of the network gives me more parameters. Increasing the depth of the network gives me more parameters. And neural networks in practice have a lot of parameters. So how do you think about them? So my favorite way of thinking about them is the following. I make a phase diagram where I put L here and I put N here. So here, I'm just imagining that all my hidden layer widths are pretty large and they're proportional to some number N, okay, a large integer. So I take the dynamical systems point of view, and I think of L as a kind of time parameter, okay, where I think of the neural network roughly as a Markov chain or something like that. Each layer does some kind of dynamics. So each layer is a time 1 evolution. Okay, and in that language, the N, the width, is then the system size. It's the number of degrees of freedom that you have. And from this point of view, it's really clear that N and L are in tension. The more degrees of freedom your system has, the longer it takes to come to equilibrium. Okay, so there's kind of 2 regimes in which people have studied related questions. Okay, so one is here you have less correlation, and this is related to the free probability regime in random matrix theory. And you can think of this by just considering the example very simple, where sigma of t is just the identity, and CB equals 0. In other words, the biases are 0 almost surely. And in this case, your model ZL plus 1 is just the product of L plus 1 random matrices applied to your input x. Okay, Okay, so that's the free probability regime. You fix the number of matrices in your product. You send the system size to infinity. That's very cool. Then there's another famous regime where you fix the system size, you study the long time dynamics of this kind of thing. And here, this is like the multiplicative ergodic field. Okay, here we get more correlation. And neural networks are somewhere up here. They're a little closer to the free probability world. They're both deep and wide. And you know, they see effects from both sides, as I will kind of try to explain. Okay, so this is just a kind of intuition, but there's a lot to this intuition, and I'll tell you a little bit more about it in a couple minutes. Okay, so let me pause. I promise to pause for more questions or comments before I go on.
Can I just double check? This analogy is with just matrices.
That's right. So if you want the most precise version of this analogy, it's like this. Although it turns out, and I won't state it, that for value networks, when sigma of t is the maximum of 0 and t, that's the most popular thing in practice, you also get an exact equivalence in distribution. If you study the derivative of the output with respect to the input, it's a product of IID matrices. That's a more complicated thing you can do. But in a lot of situations, you can think of the output as being some kind of time L+1 evolution of an input. That's all I'm saying. Okay, and we go on. Very exciting. I'm going to erase this. Alright. So let me now switch to telling you some results. And I want to first start in this regime up here, which the neural network people call the infinite width limit, for obvious reasons. Okay, so I'm going to start by saying what happens to random neural networks, although not only random neural networks, at infinite width. Okay, so what I mean, to be very precise, is the setup is we fix the depth of the network, we fix the input dimension, we fix the output dimension, we fix sigma, and then we send n1 up to nl to infinity. Okay, so you have some family of functions, some stochastic processes from Rn0 to Rnl+1, and you get different ones depending on the widths of the intermediate layers. That's the game. Okay, and in this regime, there are two theorems I want to state. So the first theorem, and I'll call this theorem I infinity. It's a very non-standard notation. So I stands for initialization. This is going to be at the start of training at infinite width. That's all I mean. Okay, and this theorem has a long history. It goes back, at least the work of Radford Neal in the 90s. Then there was work by people like Jacob Lee, lots of other people, not so, very recently something by me, where I wanted to prove a universality result. Here I told you everything was Gaussian for the weights and biases. It doesn't matter the microscopics of your Hamiltonian, if you want to put it that way, or the distribution of the little weights and biases doesn't matter. And so I checked that. No one bothered to do it. Doesn't matter. Here's the point. Okay, so as n1 and L go to infinity, at the start of training, I'm not going to write it, but that's what I mean. Here's the result. Okay, so this thing is the L+1 of x. This is a stochastic process. It's some random function of its input. Okay, converges to a Gaussian process, which I write GP, that has mean 0 and covariance kernel that I'll call KL+1, which I'll explain right now. Okay, so you get a free theory if you want to use that language. And now let me tell you exactly what I mean. Okay, so if I take the limit as the widths go to infinity, and I study the covariance, i.e. the two-point function, well, the connected two-point function, but it doesn't matter because the mean is 0, between, the ith component of the output evaluated at input x, and the jth component of the output evaluated at input x prime. Okay, that's the only thing that survives in this regime. What you get is, first of all, you get delta ij. So the different components of the output are completely uncorrelated from each other. And then you get this function KL+1 of xx prime. Okay, so each component is an IID Gaussian process with this covariance kernel. And moreover, I can tell you what this covariance kernel is recursively in L. Okay, and moreover, you have the following recursion. Okay, so K, I'll write it in general for any little L, L+1 of x prime is equal to CB plus CW times the expectation with respect to the Gaussian process kernel at the previous layer of sigma of ZLi of x, sigma ZLi of x prime. Okay, so my notation here, when I write E sub kernel, I mean these two things are now a two-dimensional Gaussian vector drawn from the covariance kernel at the previous layer. Okay, so this is like a nonlinear recursion in the layer for the two-point function of your Gaussian process. And moreover, okay, I should tell you guys the initial condition. So k0 of xx prime, by definition, is just 1 over n0 times the dot product between x and x prime. Okay, so this in principle completely determines what happens up in the infinite width limit here. I told you if you fix L and you send n to infinity, all you have is a Gaussian process. All I have to tell you is about the 1 and 2 point functions. The 1 point function is trivial at 0. The 2 point function evolves according to this rule. It's not completely trivial to analyze this rule, but okay, it was done in a series of works, including in our book. We sort of we went significantly beyond what was known before. But let me give credit to some other people. So there was a very nice paper of Lee that was early on. Okay, I did some work actually. Okay, I forgot to mention David Rolnick, but I forgot that I did this work with him as well about initialization. And then of course, the Roberts, Yaida, and the book. So what do we get? We get a particular way to tune these model parameters. You see the CB and CW coming out in such a way that as L grows, when you study deep networks, you actually get a nice distribution. Okay, so critical quote-unquote tuning of CB and CW in terms of the nonlinearity sigma, in terms of sigma, so that KL of x prime is well behaved. Well behaved at large L. Okay, what I mean by well behaved is basically that it doesn't blow up exponentially or go to 0 exponentially. You get reasonable starting points. Okay, I erased the nice picture with the orange thing, but you kind of see it back here. This is saying that the distribution over the space of functions doesn't degenerate into like a delta function at 0, or a delta function at plus infinity. Okay, and these tuning schemes are really things people use in practice. The things we recover and the things we uncover that were known exactly match what people do in practice, and if you don't do it, it just doesn't work. Okay, so this is part of the reason to study these random networks. You learn how to set certain parameters as functions of other parameters. Okay, so that's the end of the initialization at infinite width. I now want to state a theorem about optimization at infinite width. And then I'll pause again before going to finite width networks. So let me do this. State it here. And then I will promise to take questions. Okay, so at initialization, neural networks are surprisingly simple, you might say. They're just a Gaussian process. That's great. Now what about optimization? Okay, so this will be theorem I infinity, O infinity, O for optimization. So here, I'm going to attribute the theorem to several people. There's an early, beautiful paper of Do It All, actually several papers by Do It All. And there was a very influential paper of Chateau et al. Then there were some further papers. Let me also give Lee some credit here. So what does this theorem say? It says that as n1 up to nl go to infinity, gradient descent on the mean squared error, which is the example I drew before, okay, conveniently right here, that's what I mean by mean squared error, okay, converges to the dynamics of a linear model. Actually, all of optimization is linear, so converges to MSC optimization on the following model. So I'm going to call it the linearized model, L plus 1 lin of x and theta. It goes like this. You simply Taylor expand around your initialization. Okay, so you have this initial guess of x at theta of 0. That's where you started. Then plus, you have the gradient with respect to theta of zl plus 1 of x at theta of 0 times theta minus theta of 0. Okay, so it's as if you Taylor expanded your function, and you only have to optimize the linear piece. So that's kind of an amazing result, because, wow, we thought neural network optimization was going to be so difficult. But in this regime, it's actually almost trivial. As long as this is a well-conditioned matrix, you are not going to have any trouble doing this optimization. It'll be a strictly convex problem. Okay, so that's really a wonderful result. And before I close, let me tell you what the big problem is, why this didn't completely close the field. You might say, what else could you possibly hope to know? You've answered all the questions, and what are you doing? So here's a big problem. Big issue, pointed out by many people, I mean, including by the authors of these original papers. And it goes like this. At infinite width, at n1 and L goes to infinity, neurons in the network remain uncorrelated. So they start off as uncorrelated, and they remain uncorrelated, and features can't be learned. Features can't be learned. I'll explain this very prosaically in a second. Okay, i.e., you never have to relinearize your model. For any linear model like this, there's simply an interpretation saying you take the eigenfunctions of, or the eigenvectors of this large matrix. In the infinite width limit, it's actually an operator. So you take the eigenfunctions of this operator, and you're just doing linear regression for unknown coefficients at a basis of these eigenfunctions. So these eigenfunctions are often called features. And what I'm saying is the features don't change as a function of the data. They're frozen. You didn't actually have to optimize to learn them. So i.e., you never have to relinearize your model. Yeah, one of that remains unchanged, remains fixed. So that's very sad, because if you were to ask a practitioner what the most exciting thing about neural networks is, it is precisely that they learn data-dependent features. And so this regime is beautiful mathematically, and it fails to capture the most important issues. Okay, so this gives an extremely strong motivation for going beyond the infinite width limit and studying the things at large but finite values of n, and see what happens. Okay, so we don't send the width to infinity. We assume that they're fairly large, and you try to understand what's going on. Okay, so I have lots of time, so let me stop again for questions before I go on to the second bit of theorems. Yeah?
So you mentioned that this is sort of the free probability case, or
Yeah.
It's kind of hard to see that from this result because it's like a Gaussian process instead of sort of some like semicircle thing. But is it from this kernel is how we think of this as free probability?
So what I really mean by free probability is, in the relevant notion, it's a maximum entropy limit.
Okay.
All the spectra in free probability are maximizing the entropy if you just know what you mean by entropy. And similarly here, Gaussians maximize entropy. And indeed, if you study the kernel, the neural tangent kernel, or you study the K itself that I wrote down, you can study it by methods from free probability as well. You can understand its spectrum, at least on IAD Gaussian data. That's been done in a very nice series of works by people. But yeah, it was more like a heuristic that I was saying, rather than something extremely precise. Okay, I'm going to move this up, but I'm happy to have more questions if there are some. Race. Maybe people will come up with questions. Okay, so let me state some results about neural networks at finite width now. This is the thing I've been so excited about, but I need to get to little by little. Okay, so neural nets at finite width. Okay, here, just to recall the notation, we're going to take all the hidden layer widths n1 up to nl, and we're going to assume that they scale like some large number n. So n is large but finite. They could scale with different constants. It doesn't much matter. What I'm about to say. Okay, so now let me state the analog of the two theorems I stated. Okay, so what happens at initialization? Okay, well, so things are more complicated. So theorem, I guess I should call this I at width n. So here again, I should give a bunch of citations. In fact, let me give them in line. Okay, let me see exactly how I want it to state it. Okay, so at initialization, yeah, this is what I want to say. So the output of the network is no longer going to be Gaussian. It's pretty sad. Moreover, the neurons are no longer going to be independent of each other. What can you do? So you have to study the higher connected correlation functions, or the higher cumulants of this kind of thing to characterize what's going on. Okay, so there's a paper that I'm almost done writing, so I'll give myself credit, work in progress, okay? But really, this was the Roberts, Yaida, and myself book that does this, although I sort of go beyond what's in the book to some extent. and the book goes beyond what I'm able to do mathematically. But the point is the following. So let me write down the following thing. So let me consider the distribution of the output of the network. And instead of considering the distribution, I'm going to consider its Fourier transform. I'm going to consider the characteristic function of the output of the network. Okay, that's one way to talk about what's going on. And I'm going to evaluate it at xc. This is a big vector xc. So what we get is we get the following. So you write it in Hamiltonian form. So you get x. Okay, so the first order piece looks like this. You get minus, and you get c squared, oops, 1/2, c squared, and then you get k l plus 1. You know, evaluate it the correct thing depending on the inputs that you're interested in. This is just the characteristic function of a Gaussian. And that's all that survives in the infinite width limit. Okay, but now there's more terms. And so let me write them like this. So the next term is a certain constant, okay, times the normalized cumulant of the network after L plus 1 layers. So it turns out only the even cumulants survive the even connected correlation functions. And this one comes with the 1 over n in front of it. Okay, and this is the 4-point interaction. You get xc to the 4th here. Okay, and then similarly, you get some other, so maybe let me call this constant c4. Okay, you get c6, and you get kappa L plus 1 6 over n squared, and you get xc to the 6th, and so on. Okay, so what I'm saying is, this is a result which says that the 2k cumulant of the output of the network, which measures deviation from how Gaussian you are, is further and further suppressed in powers of 1 over n as k grows. Okay, that's the game. And not only do we have a characterization like this, we actually have recursions for each of these cumulants, just like we had a recursion for ki. Okay, so moreover, there are recursions. For, right up here, kappa L plus 1 2k in terms of kappa L 2j, where j is less than or equal to k. Okay, so it's like you get a hierarchy of recursions. You solve the recursion for the 2-point function, and then using that, you can solve the recursion for the 4-point function. Using those two, you can solve the recursion for the 6-point function, and so on, all implicitly at leading order in 1 over n. Okay, so the ability to do this was really actually some breakthrough work of Shou, he showed how to do this and get the 4th cumulant to come out. That was like really the inspiration for a lot of what we did in the book. So I want to make sure to highlight him and give him some credit for that. So that was really cool. But the point is you can get all of these. Okay, and moreover, so this I can now show mathematically. I can give a complete proof of this. But one of the things in the book that I don't know how to do, that some physics methods will give you, in fact you learn that these normalized cumulants, 2k, actually grow with L. These are like relevant perturbations if you want to use that language. They grow like L to the k minus 1. Okay, and what this means is that while you thought the 4th cumulant was actually suppressed by 1 over n, the 6th one was suppressed by 1 over n squared, it's actually kind of a mistake to think that. Okay, it means that kappa 2k L plus 1 divided by n to the k minus 1, which is what I wrote here, actually scales like L over n to the k minus 1. And so the main message, okay, this is the thing I want to emphasize here, message of this first part of the theorem is that depth amplifies finite width effects. Okay, and in fact, you should think of L over n as actually being the effective depth of the network. Okay, this is like a new kind of emergent height scale, if you want. And it describes how genuinely deep the networks are. So it's no surprise that if you fix L and let n go to infinity, it's as if you had a depth 0 network, which is a linear model. Okay, and that's what I showed in the infinite width limit before in these theorems. But there's a completely new double scaling limit, where n and L are both large, but the ratio remains bounded away from 0. Okay, and as I'm about to state, you actually can learn features in this regime. That's the main new thing. So the thing you were missing in the infinite width limit, you recover by actually taking large depth. And this is really the first time, this and some work I'm just about to state in a second, okay, it's the first time that I think there's a plausible story for why deep is important in deep learning. Depth actually causes you to learn features. If you have small depth relative to the width, you're not going to learn much. You're only going to have basically a linear model. Okay, so of course that's not the complete story, but I think it's a really satisfying start to a story. Okay, so let me try to finish stating this theorem. There's just one or two more results I want to state, and then I'll tell you one or two results during optimization, then I'll be done. And I promise to take questions after. Okay, so let me state one more thing. Okay. So this was done in a couple of different papers, but okay, let me only state for the moment the thing that we did in the book, and that now, okay, I'll give myself some credit for, although I'm not sure my physics collaborators would agree. Okay, it wasn't totally trivial to do it completely mathematically either, so I do this in the upcoming paper. Okay, it goes like this. If you study the variance of the sensitivity of the output of the network to the input of the network, okay, that's a classical thing to do in dynamical systems. What happens is, you actually find that it grows like L over n, well, a certain constant times L over n, okay, plus O L over n squared. And so you see that while the depth amplifies finite width effects, making the depth too large is kind of a numerical disaster. If the depth is large, you get instability. So therefore, actually, large depth gives numerical instability. Because remember, we're doing gradient descent. And so the fact that the gradients are big is really kind of a disaster. Okay, but it's not just the depth, it's really the effective depth that has to be large for this to happen. Okay, and in practice, if you actually look at networks people use, the effective depth is not too big. Okay, although the depth itself might seem shockingly large. Okay, so let me state the final theorem about what happens after training and what you can say about feature learning, and then I'll take questions and comments. Okay, so here's the last theorem. Theorem ON, okay, optimization at finite width, not to be confused with the orthogonal group. Okay, so here's the first statement I want to make. This is actually a paper with Yaida, which preceded the book and was really the first one to identify that while the depth causes the network to be unstable, it also causes features to be learned. Okay, and the result is very simple. If you just look early in training, so at the start of training, if you just ask, what's the ensemble average of the change in the Jacobian? Change in the gradient with respect to theta of ZL plus 1. Okay, this is the thing that because it didn't change, you didn't have to re-linearize your model and you never left the linear regime. Okay, so it turns out you can get a very precise asymptotic for it, and it looks like this. It looks like L over n times x of 5 L over n. Okay, believe it or not. So why 5, you might ask? Well, because 5 is 3 divided by a half minus 1. Okay, that's not a much more useful answer, of course. But okay, but the message is, you have to have a large effective depth to start learning features. Okay, and then this was for the very specific case. So this was when sigma is equal to the relative. That's this maximum of 0 and t. Most popular nonlinearity in practice, you can actually do the resummation in L over n. But in the book, we do it in general. Okay, and then in the book with Dan and Show, what do we show? We actually show for any sigma, we can say that the expectation of the change in the gradient grows like L over n plus O of L over n squared. Okay, so this is able to probe the regime where the effective depth is small. Okay, and that's consistent with this, but you don't see the full exponential behavior. Okay, and again, the message is, and I stop, large depth promotes feature learning. Okay, actually, let me say one more thing before I stop. I apologize, I meant to say something that I forgot. So in the second half of our book, this is really the first half in some sense. So really, I should give all the credit to Dan and Cho, because I didn't do this part of the book, but it's really a beautiful thing. They're able to push this philosophy of doing everything perturbatively in L over n, actually to characterize the full distribution, or like give a formula for the full network function after training. Okay, so I told you at the start of training, at the infinite width limit, wherever it is, okay, over here, it's easy to write down the formula after training. It's just a linear model, right? The posterior is an easy thing to write down. At finite width, it's not that easy, and they managed to find a way to do it. It's really kind of amazing that it's possible. It's again recursive in the network depth. And at the moment, it's hard to analyze. It's a very complex formula, but the fact that it's possible at all was shocking to me. And so I take my hats off to them. But okay. Anyway, so I think that's all I wanted to say. So I'm happy to take your questions and have some sort of discussion. Yeah.
So the perturbation theory you mentioned, when it's fully convergent, or
Yeah.
asymptotically, or what?
Oh,
Or
yeah. So what they prove is the following.
yeah.
They prove that so a priori, what do you have to do, right? You look at this change in the gradient, and you tell yourself, well, it has a first derivative,
Right.
and it has a second derivative, and it has all derivatives. In principle, if you could give me all derivatives, I could write down what happens.
Right.
But it turns out that to leading order in L over n, that thing truncates, and you only have to study the first derivative and the second derivative of the change. And then you can write down what the model looks like, and you solve it perturbatively relative to the linear model.
Right.
So it's some kind of thing where you don't have a fixed kernel, but you have a kernel according to which your kernel moves, and then a kernel according to which the kernel moves that moves your kernel. There's like a two-layer thing, but then nothing else happens at leading order. And they managed to find some way to actually write down as a function of your optimization algorithm and of the input data what exactly you'll get. And so I honestly haven't fully digested it yet. But
So it's like you don't even have to go to infinite order in perturbation theory, it just truncates it sometimes?
yeah, I mean it truncates. It truncates plus O of L over n squared. So it's perturbative to leading order in L over n. But the only things that contribute at leading order are just a finite number of derivatives.
But I mean, if you wanted to really push the perturbation theory, you'd want to take all orders into account, right?
Yeah, so that is not done. In principle, I think the techniques they develop could do it, but each order will be, I think, exponentially more painful than the previous. So if you wanted to do the full perturbation theory and then resum potentially, probably new ideas
So
are
there's
needed.
also the question of does it even converge, or is it just asymptotic?
Yeah, that's a good question. I don't think that's clear. I don't know what the answer is. Okay, clearer questions or comments?
Yeah, I was wondering which assumption you have on sigma for the very last theorem.
Yeah, so here sigma is any smooth function. Okay, that grows less than exponentially at infinity will be enough. Yeah, that would be enough. So can you do this for ReLU? My guess is when you look carefully at what they did, you can actually do it for ReLU as well, but most directly they actually tailor expand sigma in various places and have to write things in terms of some derivatives of sigma that might be higher than order 1. So they might be singular and you can't integrate them against each other and things like that. But basically if you have something that is smooth, their technique works. And you know, the technique is at a physics level of rigor in some sense, so I can't claim that I can state the precise theorem mathematically, but I very much believe that what they did is correct, and you know, you can do it somehow.
So I was wondering if I have just a zero function for sigma. Does that make sense?
If you have the zero function for sigma, well, you'll learn the zero function.
And then the expectation of the change in the gradient?
Yes, so of course I'm hiding here constants which depend on sigma and CB and CW.
Okay.
So you know, the constant will be proportional to something like, let's say, the derivative of sigma squared expectation or something like that, or to some power. So you'll just get 0 times L over n.
Okay.
So you'll get a formula, but it won't be very exciting.
Yeah, sure. But
Yeah. No, definitely. I'm sort of dropping the constants because in part because the constants are a little horrendous, but you know.
Okay.
But for sure, everything works covariantly in the right way. Yeah.
Thank you.
So the result, large set gives numerical stability. That's at initialization.
This is at initialization.
Okay. And that's different. So there's the vanishing gradient problem, right? That's different. That would be after training, and would that be contradictory to this intuition here?
No. So actually, okay, I should have said that and I forgot. So one of the reasons this was an important result, and one of the reasons that it was interesting. So together with Hanin, I didn't state this thing, or maybe I did. I don't think I stated it. We actually got the full distribution of this thing at the start of training for ReLU. Okay, and it's something that is again exponential with this 5L over n out in front. So the point is that the exploding and vanishing gradient problem is a numerical stability problem where you have very large fluctuations in your gradient. Some of them are very close to 0, some of them are very large, and no single learning rate can cause them to be order 1. And at least empirically, this is worst exactly at the start of training, before your data has had a chance to regularize the function you learn. So sometimes, especially in reinforcement learning, late in training, you actually will get your gradients to explode, and this doesn't really have much of a bearing on it. But you know, typically this was a problem because you couldn't even get epsilon better than random with these networks. They would just basically do a random walk in parameter space, and that's a disaster for doing optimization over 100 million dimensional space. So actually, this really is kind of a solution to the exploding and vanishing gradient problem, at least when phrased only at initialization, which is typically where it comes up, although not always. That's sort of how I would respond.
So this was a perturbation theory in small L over n. Can you run it around and get a perturbation theory in small n over L and sort of approach the problem from the other end?
So the short answer is, okay, it's interesting you asked that. So for value networks, yes, this works for any L over n.
Okay.
The corrections here are plus O of L over n times 1 over n.
Okay.
That's so this is an honest result.
Right.
In general, the techniques do not do any justice to that regime from the book. Now, it's worth mentioning that in the regime where L over n is extremely large, you have so much instability you probably can't train your network.
Right.
But from the random matrix theory point of view, this picture that I erased, this like L-shaped thing, I actually studied in a paper that is unrelated to what I'm talking about right now, precisely what happens at large L, like finite time corrections to the ergodic theorem.
Right.
And you can really get corrections, and you can get corrections to the whole Lyapunov spectrum of your random matrix product and so on. But the techniques that we use for that, I don't know how to apply to neural networks. And for ReLU, for example, you know, each layer has a probability of being off,
Right.
like, which is like 2 to the minus width. But if the width is fixed and L is large, then at some point you'll just be off, and so you'll be so I'm not sure what the question is to study in that regime. Although it certainly like is tempting to do some kind of duality and just go for it, but I don't know how. Yeah.
So in all of these results, sigma is just supposed to be a smooth function which is sub-exponential, or?
Yeah, so in all the results essentially except this very last one, sigma can be just even piecewise linear, as long as the derivative is defined almost everywhere. That's fine, and it needs to be sub-exponential. That's the kind of conditions. You know, because the weights are Gaussian, you just need to be able to integrate the moments of sigma against the weight and bias distribution. For this result, they needed smoothness, and you know, the kind of nonlinearities used in practice are either very smooth, like hyperbolic tangent, or this value, the maximum of 0 and t, which is just piecewise linear, and it is perfectly fine for all these results. But there are some conditions secretly that I didn't fully state. But you're right, I should have stated them if I were being more precise. Yeah.
So just going off of that, so you mentioned that you had a universality result for the infinite width limit.
Yeah.
Does the piecewise linearity of sigma come up in that because you don't know that like almost surely you're going to miss the places where the derivative doesn't?
Yeah, so the universality result assumes that you have a bounded density and you match some moments.
Oh, okay.
And then with probability 0, do you ever hit the nonlinearity of the derivative?
Okay, so it's not like a sign Bernoulli or
Yeah, that's right. That is potentially interesting, certainly for mathematical reasons. People study very much, you know, matrix products with random entries that don't have a continuous distribution, and there's actually been a lot of progress in that world. But for the neural network side, you know, people typically don't use such initializations, and so it wasn't a thing that was top of mind.
Okay.
Are there further questions? So if not, then let's thank the speaker.